Welcome everyone to a case study in climate resilient water infrastructure. This course is approved for 1 hour in continuing education units among many credentials, as well as LEED AP homes and American Institute of Architects Health, Welfare, and Safety, which may make it applicable to your state-based design or contractor license. Today, I will be your moderator. My name is Brett Little, and I'm Executive Director here at the nonprofit, the GreenHome Institute. And really what we're going to be talking about is the use of rainwater at home, the benefits of it, and what you can do from a particular case study here for some ideas for a system installation for you or your clients. And before we start, a huge thanks to our top tier sponsor, Build Equinox Serve 2 Smart Ventilation. Unlike traditional ERVs and HRVs, it features many qualities of a smarter, balanced ventilation and feedback monitoring system. With a standard HRV or ERV, you get a constant low flow of air with no relation to actual indoor air quality or occupancy. For the first 3 days when the home is occupied, the air quality is poor. The ERV just can't keep up. But when the occupants leave on vacation, the ERV keeps ventilating and wasting energy. Since the serve actually monitors air quality, it ventilates only when it needs to compared to an ERV. The serve can ventilate up to 300 CFM, quickly purging pollutants from the home when needed. When there's no ventilation that's necessary, the serve can recirculate and unify the home, providing some additional heating and cooling, dehumidification in an energy efficient manner. The serve does this by monitoring all sorts of pollutants, including CO2, and monitors your air quality. Has set points to determine for your clients on where the air quality wants to be to both fit their lifestyle and needs. Instead of the ERV exchange core, the serve uses a high efficiency heat pump to exchange energy between the incoming supply and outgoing air. What does this mean? Conditioned, comfortable air that unifies the home instead of dragging exterior rooms away from the comfort. They get up to MERV 13 now on the filtration. And the system is manufactured right in Urbana, Illinois, in a facility that's powered 100% by solar energy. It can work really well with Mitsubishi heat pumps, very well with Mitsubishi, and then as well as water furnace geothermal heat exchange loops. And they have a new UV system that they're just starting up to kill all sorts of strains of viruses. And then thanks to our second tier sponsor, Niagara Conservation. Niagara has vacuum assisted toilets that go all the way down to 0.5, depending on whether you want to use a single flush or dual flush toilet. Yeah, and they have pressure, a single flush at 0.8, which can also be ADA certified with a side handle if necessary for accessibility. And then they have shower heads and aerators now, 0.5 on the aerator, 1.25 on the shower heads. Super low flow water sense certified systems that look and feel great, don't act any different. Check them out over at Niagara Conservation. All right, well, I want to welcome our speaker today. Welcome back, Matt Grocoff. He's an American environmentalist, sustainability advocate, sustainable real estate developer, writer, speaker, and founder of the Thrive Collaborative. He is known for his work on net zero energy and net zero water buildings and for the rehabilitation of the oldest home in North America to achieve net zero energy. Grocoff is a contributor to the radio show The Environment Report, produced by Michigan Radio, Fox News Energy Team, and was host of Greenovation TV. He advocates for modernized distributed renewable energy networks and distributed water and wastewater systems that work with natural systems. So Matt, we're always excited to have you back. Thanks for inviting us here into your home. And I'm going to hand it off to you. Please do take it away.
I don't know if I invited you into my basement, right? This is the control, the command and control center of the house. This is where the heart beats. So, all right, just mandatory screen check. You see that, right?
I do, yeah.
Right, so we're good. So, yeah, so everyone, thanks for
actually, I only see half your screen. It's cut off.
Seriously?
Yeah.
What the hell? All right, how many times can we do this? And
right.
Holy crap. All right, quick ideas. Where can I
just try resharing it and see what happens.
not showing anything. Yeah, it's always fun. All right. Looking forward to seeing everybody in front of a live audience one day. So this is my house. On the right there, that was in 2006. Perfect time to be buying a house. We had asbestos shingles on the side. There's a plywood front porch. We're in a historic district, but what it had was this gorgeous, gorgeous south-facing roof. We had no insulation. We had lead paint on the walls. We had a furnace from 1957. Toilets that were 5 gallons per flush, and evidence of the old potbelly coal stoves and cisterns in the backyard and things like that. So this house for 120 years has been bringing in electricity and heat from faraway places. And in 2014, we were certified with the Living Building Challenge for net zero energy. And since the beginning, our goal was to make this house zero net energy, zero net water, and then be returning nutrients back to the community rather than taking them from the community with no waste. So here's this is the big problem here. Our current system is entirely linear, right? We've got this centralized water system, centralized energy system, and centralized food system. Our water system basically brings in fresh water from faraway places. And there's a model of my house, and the average Ann Arborite uses about 300 gallons of clean water, average household, per day. All right, and these are the different calculations of what's happening for each one of them. That water is coming from Barton Pond. It doesn't come, very little of it comes from groundwater anymore. We've got some dioxane contaminating Ann Arbor's groundwater. And the water, with all of its contaminants and minerals and everything else, gets piped up the hill with great energy, gets treated in a treatment plant using chemicals, and then leaves that plant, goes through about 500 miles of pipes, and then comes into our home and the other tens of thousands of homes throughout the city and every office building. And in that, from the source water all the way into the tap, there's the possibility that they've got these chemicals of concerns. In Ann Arbor, the things that they test for at the plant are PFAS, lead, and dioxane, among a couple of other things. These are things that are not possible in a rainwater harvesting system. It's worth noting right now. There's no way for them to really get in there, but there is a little way, and I'll tell you about that in just a minute. And then what we do with that incredibly expensive water is we pee in it. And again, it's 100% potable. Everything that comes into the house, all uses, we pee in it, we poop in it, we put our tampons in it, we drop our pharmaceuticals in it, and then we create this toxic stew that we return to a sewage pipe. So you have 300 gallons of fresh water coming in, 300 gallons of toxic water leaving the building. So we've taken a small amount of nutrients and turned it into toxic waste. And then we go through, again, hundreds of miles of sewage pipes, which Ann Arbor and many other places have tens of thousands of gallons annually of leakage, of breakage, of all kinds of things that happen throughout that process. And this is the sewage treatment plant. I think that's from Grand Rapids. And then there's a third pipe, right? Again, that's all linear, these two pipes, clean water in, crap out. Then there's a third pipe, and that's called stormwater. Couched in this really apocalyptic terms, right? We used to just call it rain. Now it's stormwater. So everything that would hit the house runs off, collects pollutants, and then goes into storms. None of the rainwater is actually used in the buildings directly throughout Ann Arbor. This is the other day. That's on Murray Court, just down the road from me. That's my friend's daughter, Zoe, in a kayak, kayaking in a 500-year floodplain in front of her house. That 500-year floodplain has flooded 3 times in the past year. This is just a few hundred yards down the road from them, inside of another 100-year floodplain where Ann Arbor is actually putting out proposals for developers to build on this city-owned land, which is profoundly bad idea. I would love to develop this. It's a gorgeous piece of property, contrary to the photograph, but we shouldn't be building in floodplains. We need those precious ecological areas. And so we can imagine now, what if we were to restore the ecological water flow of our cities and our built areas, and we were to allow them to operate in the same way and as elegantly as a forested ecosystem or a tree. So the way a tree works, rain comes down from the sky, gets filtered through the leaf system, gets directed back down into the soil, where it's actually falling softer because that tree canopy is there. And then it goes back into the soil, comes back up through the root system and gets reused to the roof. The water falling to the sides of it gets infiltrated back into the soil, and you have this mutually beneficial relationship where you're moving water and nutrients and energy all through the function of the tree. And then, of course, hugely beneficial to us as well. And then we build things around it that have just pure runoff that, again, go into a stormwater system rather than benefiting the tree. We can do the same thing inside of our buildings. Buildings can operate using the same schematic. Water can fall through the sky, be used inside the building. Nutrients can be removed. That water can be reused inside the building, just like it would be reused inside of a tree. And then after the water is done with that cycle, it can go back down, treated as clean water, back down into constructed wetlands, and infiltrated back into the soil. And then that transpires back up into the clouds again, and the process starts over again. You have this wonderfully gorgeous, elegant system that each individual building is capable of doing on its own. But a tree doesn't operate on its own. It operates in a as part of a network. So we worked with the University of Michigan Blue Lab. This is the original, some of the original members of the team. And I basically, asked them to follow the raindrop, right? And see if they could restore the ecological water flow and create a model for what a decentralized, climate resilient water system might look like. If we can prove it possible, if we can demonstrate it possible, it's already been proven, really just kind of have a single proof of concept right here in one home as a showcase. Then we can figure out how do you replicate that and how do you get that to scale? Because the ideal, again, is not a single tree, but a forested ecosystem. So what they would do is follow that raindrop. So the water comes down from the roof. These are some of the students and their things. So this, the first place the water hits is the rooftop. So they began their analysis there. First doing calculations, how much water does hit the rooftop? What happens to that water after it hits the rooftop? What is the quality of the rain itself? And what is the quality of that rain after it runs off the roof? So they did rainwater tests, found typical things you would find in any rainwater just by capturing it from the air. And then they did tests coming out of our pipe. And what they found was, and this is the rooftop here of the lab where they were doing tests on different types of roofing materials. And this is an X-ray fluorescence test. With those photographs are the actual X-ray fluorescence gun and actual chips from my roof, because the students in the rainwater coming out of our drain pipes found levels of chromium and lead inside of the rainwater. Knowing that lead and chromium don't really appear in rain, it must have been picked up somewhere between the roof and the pipe. So we tested the roof material and found that they themselves had high levels of lead and chromium and other materials in it. They had some levels of arsenic and things that you can see in this, but both the chromium and the lead, both in the dangerous areas. So that's a crappy material to be harvesting water from. And in fact, it's a crappy material to have on roofs at all, because when you think about it, we've got these materials, we've got lead, just like paint on the side of the house, covering rooftops all across America. Canada has started to regulate some of this. In Europe, they don't use asphalt shingled roofs anymore for that reason. They're made with recycled materials, but the recycled materials aren't screened for toxicity. So we went to a local manufacturer in Michigan, Matterhorn Roofing, and they were able to do a metal roof for us. The students, again, talked with the manufacturer to find out exactly what chemicals are in the coating. and then did tests on that. And we use only red list free. They only use red list free materials using Galvalume and other things. So it's a really good, clean roof surface. And you can see there, the roofer is actually installing this over the existing asphalt shingles. So we're just kind of embodying that lead and that carbon into the roof. And then we put on, this is a gutter guard from Leaf Blaster, I think it was called. They sent us these to filter out the larger leaves and things like that, and the water still gets filtered right into the gutters. The gutters go in. This is from Green Oak Gutter here in Ann Arbor. Again, this is Galvalume, stainless steel. So it's coated with that material that, again, is red list free, and I believe has a declare label from the International Living Future Institute. And then it goes down in those pipes and then enters what's called a VISI system. This is a system out of Germany, which just basically just uses a cyclonic pathway from the pressure of the water coming down from the things. A bit of it overflows, and then the other parts get microfiltration through before it enters the rain tank. So you get very, very little sediment going into the rain tank, but the water is still a little bit turbid and still might have some biological materials and stuff. So this is the tanks being delivered. It's one of the Blue Lab students. And those are the tanks being set into the ground. So you can see this is not simple work. And those tanks obviously get buried in Michigan here below the frost line. In Hawaii, these tanks can be above ground, and many other places in the South, you can plant these above ground. Here in Michigan, we have to bury them. And you can see over here in the middle of the screen where the pipe is coming down, and then eventually that gets tied into the system through the VISI system. This was uncovered. This is the remnants of the original cistern that came with the house. So originally, this house harvested rainwater off of the roof, and so it had basically a dual plumbing system. One, a hand pump in the backyard going to a well where you got fresh water, and you only needed to bring up a few gallons a day for your drinking water into the house. And then the rest of it for washing clothes and dishes and watering the plants and everything else was harvested rainwater, and it was untreated. And you can see this little pipe in the middle here that went directly into the basement, which went into upstairs into the dining room, where there would have been a hand pump on a little sink. The dining room now used to be the kitchen back in 1901. So they would have had a little hand pump there, bringing water directly up from the cistern to use in the sink. And again, their fresh drinking water they would have gotten from outside or boiled it on the stove on the inside. And that's what it looked like shortly after the install was completed. Those are the covers for the tanks. And that's my daughter harvesting basil right next to those covers pretty recently. So we put a garden on top of that tank. And so that's what it looks like now. So this is the room that I'm in right now. Yeah, Brett,
hey, man.
Yeah.
Yeah. Is there a reason that you went with buried tanks over? Did you consider just putting the tanks in the basement at all?
Yeah, we did. And we could have done that. The challenge there in Michigan is the thermal issues that you have with that. If you've got snow melt in the wintertime and you're bringing in water that's 35 degrees from or even 50 degrees, frankly, from under the ground, as that water's getting flushed through, the faster you're using it, the colder that water is going to be, because it's not going to have time to warm up underground. So if it sat there for a while, it would equalize with the ground temperature. So basically, you'd have a big thermal sink inside of your house, and it would be pulling heat from your house and heating up the water that would then come out of your pipe. So now in the summertime, that could have a great cooling effect.
Right.
And that would be really beneficial. But just doing some calculations here and figuring out, but that was the original plan, was looking at doing it in there in the basement. And then you also have the other issues of what if it does leak. The likelihood of a leak in these tanks is exceedingly rare. I've actually never heard of one that did, or I don't know anyone personally that did. but still, so in the basement. But again, that is a possibility. And if the house is large enough and you have an area that is, we did consider that for another building in downtown Ann Arbor, where they were going to use the huge storage tanks to recirculate for indoor pools and spas inside of the building. And so that rainwater was then going to be used for cooling and things throughout. So they wanted that heat exchange in the building. But that was buried under the building inside of a concrete basement that was itself insulated and thermally separated from the rest of the building, with pipes going in through and doing a thermal exchange, basically having their own lake inside the building. I think we called it like a thermal lake is what we called it. So yeah, so it is possible to do.
So I just want to make sure I heard that right on the first one. You were saying the cold water coming in the winter would actually steal the heat from the house potentially. Is that what you mean?
Yes. Yep.
Yeah. Interesting. Okay. Thank you.
Yeah. Basically, you imagine bringing in a big ice cube from outside in the wintertime and sticking it in your basement. What do you? It's not a.
Yeah. That's a new one that I've heard. So yeah, thanks.
Yeah.
Oh, and so somebody commented, could you not just run longer pipes underground before bringing the water into the basement to equalize the water ground temperature?
You could. It would probably take a pretty decent length of pipe to do that, and then you may as well bury the tank outside. So yeah, you could do that.
Okay.
It's interesting because this thermal exchange is really important. So I got upset with Kohler a few weeks ago, but
you're live.
It's not Kohler's fault.
Okay.
So actually, it's been over a period of months. So we have one of these, really fancy, expensive faucets that Kohler had sent to us to try out, and we were getting. Oh gosh, I shouldn't tell you this because, okay, this is on a test tap that we have actually, not on the Kohler faucet. And so that water, when it's connected to the hose outside, and if the tap is open outside, because it's a closed loop system, we had the hose and it was almost 100 degrees with a heat index outside. The tap outside was open even though the sprinkler wasn't on, so the hose was filled with water that was then connected to the water inside the house, and it was in the direct sunlight, and it was so damn hot outside that it heated up the water that was inside of the tap inside the house. So yeah, so
helpful in the winter.
Exactly. I thought about that. I was like, well, why don't I just do this? But it wouldn't be as cold in the wintertime.
Yeah.
So this is the water room. It's actually a really simple system. These things you can buy similar systems in Home Depot. This one comes from Reynolds Water. University of Michigan College of Engineering graduate Jamie Reynolds worked with us on this and provided all the equipment for Blue Lab. But again, this is not rocket science. This is the same type of system that they would have at a centralized treatment plant, but shrunk down for a household. It's the same kind of system that you'd have in a restaurant or a coffee shop to get some of the highest quality water that you could get for brewing coffee and things like that. It's really just a 3-stage filtration system with carbon. So again, there's a University of Michigan and Blue Lab, and of course Forbo donated the floor. Sorry, US GBC, for keeping that logo in there, but it's on the floor. So this is the pipe coming in from the tanks. Again, this is untreated water directly from the tank. So while it doesn't have minerals or any kind of heavy metals, it could still have biological contaminants and things that get on there from the roof. And we have this water tested frequently, and we know that it does have some biological contaminants in it, like any standing water would from a natural environment. Then it goes through Grocoff compressor into a pressure tank. The pressure tank pressurizes the water in the pipes to, I think we have it set at about 60 degrees or 60 PSI. And then it goes through those 3 stages, first through the larger 50 micron filter, then down to a 5 micron filter, and then down to a 1 micron filter. And at this point, the water is pretty darn clean, and for the most part, it's drinkable. You still have the danger of some other biological contaminants being in there that would not be killed or filtered out through this system. Then it goes through through a carbon filter, which really gets out any remaining residue. So this is the same kind of carbon filter that you would have in your little Brita filter, or that they have in the centralized treatment plant through that carbon filtration stage. And at that point, there's still a little bit of carbon residue that's left in the water. So just for an aesthetic and for turbidity, really, there's another small filter that filters out the particulates of carbon through that. That's also important because the next stage, you want the water to be as clear as possible, as non-turbid is the technical term, right? So turbid water, UV only works if the water is clear. So you don't want particles. Even if the particles themselves aren't unhealthy, they might be blocking the UV from attacking particles that are unhealthy. And the UV has an alarm that if it's not clear, if the water is too turbid, it will let you know that the water is too turbid and the UV is not going to be effective. But as long as the water is clear, and it always is once it comes through this 3-stage filtration, carbon and then carbon filter again, once it's clear, the UV kills all remaining life basically that's inside of that. I forgot the gallons per minute that this can handle, but it's quite a bit, more than our pump is capable of pumping through it. So what comes out of there is purely scientifically potable drinking water, and we've had this tested multiple times. We get it tested on a fairly regular basis. And then this is the UV Max monitor that connects to the UV system itself, and that the 220 is the days remaining until it comes time to replace the bulb. And we replace the bulb just annually on a regularly on a 365 days. We replace the bulb, whether or not it needs it, just to make sure that we're always having the highest quality protection that we can. And then having it tested intermittently between that. And then it comes out through the final pipe, and we've got a little test tap there. We are required to label this as reclaimed water. And then we have to put it through purple pipe. So anything that's being delivered to, even though this is scientifically potable water, by any measure, NSF standards, this is drinkable water. The city cannot classify this as potable water because there is only one type of water that can be inside of municipalities in Michigan, and that is municipal water sources. So the reason for that is so that we can socialize our water systems. So, back in the 1920s and 30s, when they were putting in these centralized systems, you wanted to make sure that everyone got off of the wells and started using the system to help pay for the system. And the system doesn't get paid for through tax dollars for the most part. It gets paid for through use, through the billing. And that's why in Detroit, they're having so many problems, because when the population declines, the volume of water that needs to be treated remains the same, but the number of people to divide the billing and the cost by goes down. And so the cost per customer goes up. Population declines, cost per customer goes up. So huge equity issue here, that the poorest areas with declining populations actually have the highest water costs in the nation. And so you can't use this water for potable services, for services. So we can only send it to here where we've got these labeled, to the irrigation outside, to the spigots, to the toilets, to the washing machine, and things like that. So this just took this picture a little while ago. We're washing our water with rainwater. We also, again, we have to label it as "don't drink it." So I found this creative sign to warn people not to drink our toilet water. Technically, I think we're supposed to have that sign up all the time. But I think what we should do instead is make everybody else in Ann Arbor put up signs on their toilets that say, we use city potable drinking water in our toilets, so feel free to drink it. That'll make a really good point. And then we are required to be connected to the city supply as a backup in case we ever did run out of water or in case of a failure of the system. We don't expect that to ever happen, but in case it does, we are connected to the city supply and we're required to have a backflow preventer. And what that does is if the system were to fail and it was connected to the city supply, there is the potential that contaminants from our system could back up into the city system and contaminate the entire city system. Their water is treated with chlorine and other chloramines and things, so it's not likely, but because it's possible, they do require this backflow prevention system. The system is off, it's not connected, so there's not even the possibility that water could go back into that. But if we ever needed it, we could turn it on and have a direct connection to the city supply. So here's something I just pulled up this morning. This is from the city's most recent report to its residents. These are the things we test for at the city. Things like alkalinity and aluminum, ammonia, arsenic, calcium, all of these different kinds of things, sulfates, potassium, lead, mercury, magnesium, zinc. These are all things that are not possible in rainwater. They're not found in rainwater. You're not going to get calcium or iron or lead or magnesium inside of rainwater. You might get mercury if you're near a coal plant somewhere in your rainwater, so that would need to be filtered out in some systems. In Ann Arbor, we have yet to find any trace of mercury in our rainwater. Again, with these decentralized systems, that is something that we could eliminate, is the need for these kind of things. Really cool, actually, is recently I had to do some plumbing upgrades, and when I was pulling off taps from the city supply, I was having to replace some valves and things that were all crudded up with calcium deposits, right? It had all that white calcium all around. And Ann Arbor's water is actually really good. So, but we still had calcium buildup around these parts. And so I had to replace those parts. The rainwater pipes didn't have any of that because there's no calcium. So you can't have calcium buildup. So the parts are going to last longer because they don't have the degradation from some of these other minerals and things that are in the water. So, and then the third pipe, that we don't have is stormwater. We are sending no water from this property into the storm drains in Ann Arbor. 100% of our water is infiltrated back into the property as if the building had never been built. This was our original driveway, and you can see when the gutters, hit the lead roof and all the lead comes down into that, it goes onto the side there. You bring in your SUV, park it in that driveway. You've got leaky oil. All the water picks that up off of that dirty asphalt driveway and sends it into the storm drains. We tore up that driveway and we replaced just the skirt at the end for aesthetics with some cobblestones from streets in Chicago that were removed. That's Belgian stone, by the way, that came over as ballast in sailing ships. And then on the right side there, you can see we're prepping for a green pathway and parking space for grass pavers. And at the top, using the same material, this is an eco-raster material, so you can see the truck on the right. And again, both of these systems are rated. You could drive a garbage truck or a dump truck filled with stones. This is commercially rated surfaces here. And we did that not because we needed it, but we wanted to prove a point. Because in our neighborhood like Viridian and things like that, we'll be using some things like this. We'll be making fire lanes where a fire truck can come and drive onto this surface, even if it's grass, and it'll be perfectly stable. And yet it's 100% permeable. So this is my 80-year-old mom walking on it with her cane. You can walk on this surface with high heels. Again, on the right side, that's completely permeable. It's grass growing through it. which is a challenge to maintain because you're trying to grow grass in a surface that you want water to flow straight through rather than hold the water the way grass wants it to be. So that's something to think about when you're doing grass pavers like that. And then on the left side, that's the stone version of that, which is basically can hold like 2,000 gallons of water underneath that, which you'd have to have a whole lot of rain on our property in order to get 2,000 gallons of water into that surface. So an extraordinary amount of water that it can hold. And so here is us just spraying water directly onto the surface. And you can see that water's flowing at 5 gallons per minute. And it's going straight through. There's zero puddling. It doesn't matter. We had a rainfall the other day in Ann Arbor that was pretty catastrophic. We had over an inch in 20 minutes, and there's no water on my driveway during or after that rainfall. So all of that water is going directly into the aquifer adjacent to our house, and cleaning the water. So this is an example. So as we were installing our decentralized system, the neighbor across the street waited for a catastrophe to happen, and they had issues with their water sewer pipes, and they had to dig up their entire front yard and replace the pipes. So this is the workers in the street connecting to the city utilities. And so you can imagine if that had been under their driveway, you're talking over $10,000 per household to repair this type of thing. So this is a cost that is not taken into account when we do our water bills. This is paid for by individuals. It's paid for by tax dollars, by other sinking funds, by all kinds of other mechanisms. It's not calculated into the cost of water. So there are folks now just really looking into what is the true cost of delivering water. Ann Arbor does an extraordinary job of providing fresh drinking water to the city and its residents, but we rely on a really poor designed linear system. And if we fail, we're going to fail catastrophically the way Flint did. But with decentralized systems, you fail much more gracefully. You have many, many smaller parts that are adaptable, easy to fix, easy to upgrade as the technology improves, and you can scale them up and you can scale them down, and the cost remains relatively the same, because if you have more people, you can add more component parts. If the city shrinks, you can take away some of that old infrastructure and make it smaller, just like a forested ecosystem would do. So this is don't even try to read this. This is just an Oregon roadmap. These are the code barriers to doing a lot of this. What this shows is each one of these little squares with orange lettering in it is a code tied to a specific fixture inside the building that is regulated. Some of these are city codes, some of them are state codes, some of them are county codes. So when the rainwater comes in, you can send it to a toilet, but you can't send it to a shower. Where the water comes out of the toilet, you know, that's regulated in another area. And so you can see just this mess of code regulations. So this is changing. I think it's gonna go very slowly, and then all of a sudden, like all other good change does. But we're starting to see examples all over the world of these buildings that have their own built-in infrastructure. This is the Candida building at Georgia Tech in Atlanta. It just opened pretty recently, actually during COVID. It's operating really, really well because nobody's in it. It's a net positive water building and a net positive energy building. So it's harvesting all the water used in that building is used in it. So you can see here how they were able to work with the city, and they're a college campus, so they had a little bit more leeway on how they did their code. But again, this system here mimics exactly that tree diagram that I showed you before. The rain falls from the sky, it's harvested through its canopy, the flow is softened until it goes into cisterns. It's treated, but it's treated differently for different types of usages. So it's going into the water system, into the toilet system, They actually have a waterless system that uses very little water. Then condensate, so it's actually evaporating, so it's transpiring, just like a tree would do. And then it's reused inside the building and then infiltrated back into the ground through gray water treatments and through bioretentions. And so you're taking site runoff, you're taking the stuff from the building, and you're recharging that aquifer. So the purple here is recharged from inside the building. The blue is the stormwater runoff from the building. This is another building. This is the Birchie School in Seattle. Again, net positive water. The Bullitt Center. There's literally hundreds of buildings around the world that are now using this more modernized infrastructure. This is the Burbeck farm right here in Ann Arbor. Tom and Marty Burbeck. And if you guys if you're in Michigan and ever have a chance to tour the Burbeck home, it's Michigan's only fully certified Living Building Challenge building. And it's extraordinary. Again, it's harvesting all of the energy that it needs on site, just like a tree or a flower would. It is harvesting all of the water that's used inside the building, and all of the nutrients are used on the property. They're not sent into any kind of sewer pipe or anything like that. And then clean water is returning to the aquifer. So that's kind of a big overview of things. So if you want to take my screen back and we can start a little dialogue here.
Yeah. We got a ton of questions coming in, and let me real quick here before we get to those questions. I just wanted to briefly, for everybody, go over how this all fits within the LEAD program and how they can measure and evaluate rainwater. So let me make sure I cover that. I was actually still putting that together here real briefly as you were talking.
While you do that, yeah. If you can keep my screen, I'm gonna go get a drink of water here. While this is not a potable tap, the city can't prohibit me from drinking it. And I'm thirsty.
Did you have the city water with you too to show it side by side?
Water, yeah. Thanks for asking. So this is not typical. Again, like I said, the city of Ann Arbor actually has very high quality water. They do an extraordinary job, and honestly, I have some of the smartest folks you'll see. But I don't know if you can see that, but this is water that we took out of the tub one day. It started running red, and I wish I could backlight this so you guys can see it. Are you able to see that, Brett?
Yeah.
You can see the sediment there at the bottom. We actually never got this tested, but the assumption is that that's just iron from the city pipes in front of the house. We don't have any iron pipes in the house. We don't. All of our piping is PEX, so this couldn't have come from inside the house. So this is obviously from the city itself. So I went to draw a bath for my daughter. This came out. So you often can get manganese, iron, and things like that in municipalities. I grew up in Atlanta. We commonly had red water flowing out, and this is, the drinking water from the rainwater. So,
bottoms up. Well, real quick, yeah, we got a lot of questions. I got some more questions too. Let me get through a couple things here. I just wanted to let everyone know, from a LEAD standpoint, water in, water out, rewarded, measured, verified. Quick on the intake side, total water use. So think of it this way, we're all accustomed to energy modeling. The future now is water modeling. We can design, build homes, buildings, renovations, you name it, and we can start to account for how much water they're going to use and put together a water budget. So there is a performance pathway that is optional under LEAD and can be used for its prescriptive path as well instead, where you can actually discuss water savings with your clients and measure it based on the inputs from a whole showers, lavatory, toilet, clothes washers, dishwashers, and then outdoor water usage as well using the WaterSense program. And then you can pick up points within your program through the lead aspect. Now, where rainwater comes into play, it's still kind of a Wild West approach. So here's a snapshot of the checklist. They have a piece in there for both gray water and rainwater. And so that's where you would put in the information that you have on how much water you believe it's going to generate. Think of it as renewable energy, right? Think of the rainwater as the solar energy hitting the house for an energy system. Rainwater's offsetting your efficient usage of water. And so that's where you input that information. Now, if you look at the guide on their website, you'll see how that gets verified and submitted is still open to discussion and interpretation, and they don't have any formal way of doing it. And WaterSense Water Budget doesn't either. So currently, two different ways, system and project consultants. So when you're doing a rainwater system, you might have an architect for it, you might have an engineer, you might have a manufacturer. So you can use their data and their information as long as they can just back up how they did it. Conversely, what I'm really excited about is the water efficiency rating score. Think of it as a miles per gallon label that every home will have in the future for water usage. New homes, existing homes, multifamily, hotels now can use it. And so this is a tool that can be used and that uses science and water calculation data from around the country, airports, to verify how much water a site might be able to collect from the rain, among many other efficiency features. And so you could use a report like that. And I think we have a lead home in Chicagoland that is going to be using that for their rainwater collection system. So check that out. Now, on the outflow side, like Matt said, very exciting. You can take that rainwater, you can use it in the house, and you can stop it from hitting to the stormwater. And so that's another great aspect here for the rainwater management credit, low impact design. So you can think of all the different strategies, many of the ones Matt talked about, porous concrete, vegetated roof, gardening, anything that's going to capture that water, keep it out of the storm system. Even capturing it for rainwater can be used to get points in the lead system. And so here's sort of the calculator. So you're going to need to work with your landscape architect to be putting in all this information of the size of the house, the permeable paving square foot, hardscapes, you name it. And that's where you're going to get your percentage of water managed on site and can pick up all of your points that way. So yeah, let's get into those questions. Just real quick, for those of you who want your Con Ed, check your inbox for the certificate, take the survey. The survey will be popping up at the end too, so take it then. For those of you watching this in the future on demand, get that 80% passing rate on the quiz. And then to find the quiz on our website, click on the YouTube link. Go to the left there, click Show More below the video, and then on the right, you'll see a link to take your quiz and get your Con Ed. And again, a huge thanks to all of our board of directors, our volunteers, our sponsors. Big thanks to our top tier sponsors, Mitsubishi Electric, Build Equinox, and Ream. Thank them for their support. So yeah, Matt, real quick, I wanted to go back to where were we at here? I think when I think of filtration for water, you named off your system, and I was surprised to not see reverse osmosis or RO, because I always feel like that's sort of the gold industry standard to protect us, right? It's always getting pushed by the water companies to get these RO systems. So do you have one at your tap as sort of a last line of defense? It didn't look like you had it in your system. No. What's the reason that you didn't use it?
No, first, there's a gold quality standard, and there's different types of filtration systems for all kinds of different qualities of water. So you've got your potable water, and there's actually multiple systems that will get you to that level of potability. So reverse osmosis is not going to get you better quality of water than what this system has. But what reverse osmosis uses more energy and it does have some water waste as well, because it's pushing water so much. There's simpler systems than the reverse osmosis system at this scale. So that's why we chose not to use that. That's not a bad system, but it's perfectly fine. And then with the UV, that's just another technology to kill bacteria, and chemical free as well. So that's one of the things with Living Building Challenge is figuring out how do you get to chemical free filtration. So you've got these three different stages, or multiple different stages of water use, right? You've got your I'm going to treat it to potable standards, but you only want to treat to potable standards things that are going to impact human health, right? So we're putting potable water into our gray water plumbing, which is really dumb, but that's what we're allowed to do in Ann Arbor. And in fact, we're not actually required to have the UV light on this because you're not supposed to drink the toilet water. So we're not required to have that, but I wouldn't want to do this every day, drink the water, if we didn't have that. And so we have that as a backup, and also just kind of demonstration of how that works. And then there's gray water. So that gray water is non-potable source water. So that's going to be for your washing machines, your irrigation, your anywhere where you're not touching water to your mouth, right? And then there's black water. And the black water is anything that's going to have biological contaminants in it. So your dishwasher, which could have salmonella and things like that coming off of, or your kitchen sink, and your toilets. So those things, you can treat the water, the bacterial stuff, through a gray water system, membrane bioreactor. Like we have an Aqualoop system that we actually did not install. By the way, if anyone wants to buy one, I have one here. They'll sell to you for half price. Will not get it cheaper anywhere. It's brand new, unused. So that's the Aqualoop system. And what that would do is harvest the gray water. So the water coming out of the potable water that we used and is coming out of the sinks and the showers and things. So it's still relatively clean water, but it passed through, washing us and things like that. And so that will treat that stuff to gray water standards. You could then add a UV light onto the end of that and make it potable. But if not, then that can be reused into the toilet. So you can take the water from your showers, your sinks, treat it through a membrane bioreactor, send that back up through a gray water system and into your gray water pipes, into the purple pipes. So it's called a dual plumbing system. So that alone, without a rainwater harvesting system, would reduce water consumption or the need to produce so much potable water by huge amount in any building, in any municipality. And then there was a fourth one. What's the fourth one? Oh, and then infiltration. So then what's the quality of water that you want to infiltrate the ground? And depending on the municipality or the water district who has regulation over what can I put outside into the aquifer, what can I put into a constructed wetland underground and let the water from the house that's been used leach into the soil, and there's a level of water quality there.
Speaking of quality, somebody had asked, do you know the pH, or did you investigate the pH of your rainwater?
Yes, and we have it, and I don't know what it is, but it's not, I don't have it off the top of my head, but yeah, it is something we test for.
Probably not concerning.
No, not at all.
Going back to gray water, what's the reason that you chose rainwater over gray water, or why not do both?
Well, ideally we would do both, but because of regulations inside the city, we're using, ideally the system would harvest the rainwater, treat some of it to potable standards, or all of it, but just harvest less, and then send that to the potable pipes, right? To the blue pipes. We would then be able to drink that water, shower with it, wash our hands with it, and everything else. All of those drains wouldn't go into the sewer. Instead, they would go into a second system, which is a gray water system. And in our house, that would have been a membrane bioreactor. There's other kinds of gray water systems. It could have been through another filter system like this in the back, just without the UV. So you could do that. But again, you want to try to target the lowest energy intensive system you can. And then that water would go into the purple pipes, which are used in the toilets and the non-potable taps, the irrigation and things like that. And then that's when those signs become very important, because you don't want to be drinking out of hose water that is not treated to the same standard that this system is treating it. So ideally we would have that, but because we can only use this system for the gray water in this house, if we were to then reuse the gray water, we would just have too much water. So that's why we ended up never installing that system.
How much water would you need if you were able to use non-city water for everything that you have? I mean, do you track all that, or are you?
Yeah, we could have. The numbers worked out to where we could have been net positive water for sure. The math is there that it is feasible. And you know, Frank, and that's with very little conservation methods. I mean, we've got we've got our dual flush toilets, which we only use the lowest flush. So we use the Caroma, which is a 0.8 gallons per flush. We've got Caroma shower heads, which are, you know, one of them is 1.5 gallons. Another one is a Bricor, and that's 1 gallon per minute.
Right.
You know, a gallon per minute in our guest shower, and no one's ever known that it was a water-saving fixture.
Right.
So yeah, so in those ways we do save water, but I don't tell my daughters to take shorter showers or anything like that. We do very little water conservation. You know, we've got a WaterSense washing machine from Whirlpool, but so we're, you know, common sense things that you should do anyway. But we're not bathing in our pasta water. We're not using the gray water, and yet still we're using generally under 50 gallons per day from the city. And that's without any water conservation, or very little water conservation anyway. Again, things that should just be common sense. So
in your city, you were telling me the other day, it sends you a pretty cool report on your usage, right? I mean, you kind of get to track all that.
Yeah, we're able to get really neat water usage. So you can get daily. Ann Arbor now has a website. I can get a text every day that tells me if I've exceeded a certain threshold that I can enter. So you can say, tell me if I use more than 100 gallons a day. Tell me if I use more than 50 gallons a day. So we have it set, tell me if I use more than 50 gallons a day. And so every few days, every few days when we're doing tons of loads of laundry, when everyone showered in the morning, then went to the lake, then came home and showered again. You know, so we had 4 people, and you know, one of those is a tween. So they're taking fewer baths, so you can see water consumption drop when they're not taking baths. But on days when they're taking baths, I mean, 30 gallons right there for a bath. So yeah, and again, these are, you know, energy savings as well when you're using water efficient fixtures, because you're using less hot water in those ways. And I really wish we could connect the you know, one of the issues with water heaters is and heat pump water heaters is, you know, calcium buildup on the heat exchangers, right? And with rainwater, we wouldn't have that issue. And so someday I would love to be able to hook it up to that. We haven't really had much issues with calcium. It's not that high in Ann Arbor, but it's enough to be annoying. In other areas, it would certainly be enough to be more than annoying, but problematic. And again, that's just one of the many things that gets eliminated from decentralized systems.
You talk about energy use. I mean, I know you track a lot, all your energy down to the kilowatt of everything. What's the pump there in the system using UV light and everything?
A lot. So water is highly energy intensive. So municipalities across the country, street lighting and water filtration systems are there, and clean water are the highest energy consumers in every municipality across the country. Hugely energy intensive. And so a pump and a UV light are people who are doing net zero homes and fail to account for the pumps are often astonished, or they used to be anyway. Hopefully they're not anymore. we installed this afterwards. So we're actually with that system, with this system, we're not net zero. We were intending, the plan was to put up more solar to account for this, and we haven't done that. So that'll happen soon enough. For us, you know, we don't pay a utility bill anyway, so it's there's no economic incentive for us to do that right now, but we will do that.
Well, let's head out
for the electric car. So
right. Heading outside, I was wondering if the system that I mean, obviously we see all sorts of permeable systems. We see stormwater management systems, but we don't see them too often where a part of that system is rainwater catchment. Do you know, I mean, is there a I guess a cost savings or a labor savings if you use part of the rainwater instead of if you were to just said, hey, I'm going to divert all stormwater, but using my rainwater in my house isn't going to be a portion of that. Do you know what I'm saying? Like, did you think through that at all, or?
So, no, I'm not sure exactly what you're asking.
Well, what I'm saying is you're clearly capturing rainwater in tanks that would have otherwise been stormwater.
Yes,
and I assume had you're not doing that, you actually wouldn't be at 100% stormwater retainment, right? I mean, if you weren't capturing water in tanks.
Correct. Absolutely. Right. Because it would go somewhere. Well, we could have. I take that back, because theoretically, with the rain gardens and the driveway, we could just divert the downspouts directly into the ground. And we could still we could still avoid all runoff. So that's just one issue, avoiding stormwater runoff. At Viridian, we're doing that. The entire neighborhood will be keeping all of the water, infiltrating it back into the aquifer with the possibility for overflow if needed. Yeah, and that's through all kinds of different strategies. We're working with Biohabitats, who did that little diagram you saw from the Candida building. So we're working with Biohabitats using all kinds of different strategies. So we're using bioswales and rain gardens and catchment systems, and we're even going to find ways of taking like water that's stored underneath the parking lot that's slowed down and then goes into an overflow. So it's held there temporarily and then goes into an overflow if there's a higher rainfall event, of using that water. So we're looking into being able to harvest that water and using that to flush all the toilets in the neighborhood. So the water that's captured just under the parking lot of one commercial building in the neighborhood should be able to be enough to supply at least all of the toilets in the neighborhood. And we'll be able to do that with simple pumps and again, just converting that to a pipe into a gray water system. And then if there's a rainfall event, we'll actually be able to open the valve and let the water out and empty the tank before it rains, so that we can still keep that in the calculation of rainfall. So it still serves two purposes. It eliminates the rainwater runoff, and we're using that in between during that cycle.
Right. Someone commented, love the driveway, but how do you shovel the snow off of it?
Oh, it's actually really easy, because all the stuff is, well, the answer is I don't shovel it, I plow it. I have a little Ego snow blower. Any of the Ego stuff, they're mind-blowing. It's better than any kind of gas thing you'll ever use. So we have a mower, and in fact, I was telling you, apparently people are taking all their little electric blowers in Portland last night, and they were blowing away the tear gas from federal troops. So these are the joys you can do with electric blowers now. So yeah, so we have a plow, and it's all plowable. So you could actually run a street plow or a sidewalk plow or snow blower over that surface. So it's ADA compliant and plowable. Yeah, and you can and it's a better surface in the snow as well. So when it melts, it goes into the driveway instead of melting and then freezing on the driveway. So it's a great surface for the snow, to answer your question.
So somebody was asking, and I don't know if they're talking about just under the driveway in general, or if they're talking about in the tanks, but they said, is there ever a problem with water getting stagnant under there?
In the driveway?
Yeah, and again, I don't know if they're talking about just the well, yeah, your tanks aren't in the driveway, so yeah, under the driveway. Yeah.
Well, I can address both of those. So no, because it's flowing. So it doesn't stay there. So it's not a catchment system. So the water goes into the driveway and it's actually tilted, however many degrees that looks to you. It's about this much away from the house. So the driveway, interestingly enough, is actually flat level, which is really cool. So you can have a level surface above, which you can't with an impermeable driveway.
Right.
Underneath, there's the gravel goes, it's about 18 inches down. So underneath it flows this direction, and there's a textile underneath at the bottom that is permeable, but some of that water will still flow. So some of it will trickle and seep through and go straight down. Most of that water flows over into the rain garden away from the house. So we could have pretty catastrophic rains, and that water is all going to go underneath into the rain garden area. It's actually a prairie area next to the house, a constructed prairie, and that's going to go through. We're on great sand on this property, so that's the other thing too. Section by section of every piece of land, you're going to have to do soil borings and see where the good soils are. So where the system we have at Viridian, when we're talking about 9 acres of this, is pretty complex. So the soil is, there's clay, there's sand, and you want to make sure you're moving it to where the good soil is. Yeah. It's much more complex than a centralized system for sure. If we were to put storm drains in Viridian, it'd be very simple. You could do it in an afternoon or two to design it. You just take all the roadways and you put a pipe in the ground, and it's very linear, and you slope everything in that direction and use the road as a drain. And then it goes out to Platte Road, where it would go into a city stormwater drain, and then the city takes care of it. That's a really crappy system when you think about it, because it has to operate perfectly at all times. Whereas more natural systems can have many, many points of failure and still not fail systemically. Whereas a linear system is fracture critical, which means that if one part fails, it can impact the entire system. So if you have a pressure drop in the water supply coming through a neighborhood, you're going to have a boil water alert in that neighborhood, because bacterial contaminants can go through every single home. Can have that problem. So, yeah.
So we all kind of know the term net zero water, obviously, not really not taking any water from the municipality over the course of a year or season. But what about net positive water? I think you might have said that, and someone's asking kind of what does that really mean?
So net positive water is the whole shebang, that everything on your site. So those building examples that I gave you, and again, code in most municipalities doesn't allow for all of this yet. Not that the science isn't there, it's that matching those old codes with each fixture isn't there. The complexity of it hasn't been addressed yet. So net positive building is basically the same thing as energy. All of the water use on site has to be harvested on site. And then the water has to go back to where it would have gone. So you have to restore the ecological water flow. So it has to go back to where it would have gone if the building wasn't there, so pre-development. So if that rain would have hit the ground and gone into the aquifer or flowed over somewhere else into another river or stream, that's where you want the water to go after you're done. So, and then the black water has to be, you can't have black water coming out of the property, right? So there's no sewer taps. So that would go into a nutrient recovery system. The old school composting toilets aren't a thing anymore. The new composting toilets are really just engineered systems in order to recover nutrients from that system. So inside the Candida building, or the many, many public buildings around the country now have it. the Omega Institute, the Center for Sustainable Landscapes, the Phipps Conservatory in Pittsburgh, a lot of places. They'll go into these systems that take the waste from the toilets, convert it into nutrients, and the nutrients are removed from the property. Some of them have urine recovery systems, so nitrogen recovery systems. So really incredibly, the highest quality nitrogen you can get is going to be coming out of this urine and can be harvested. And if you imagine if we did this all over the country or all over a single city, the amount of nutrients you could collect from residential and commercial buildings would be extraordinary, and they could be distributed either at a low cost or free to local farmers. So that's what net positive water is that you're actually, the water, just like it would be in a forest, becomes a benefit to not just the occupants of the building, of the organism, but to all of the other organisms and systems around it. So it has a positive impact on it, not just a, so you're returning more than you're taking away.
Right, right.
Where the opposite is net negative water, which is what we're doing now. Taking water from a river that we pollute the river. Then we take the polluted water from the river, we pipe it up into a building, we treat it, tons of energy, tons of chemicals, highly engineered, back through these pipes. The pipes are old, outdated. 70% of them in Ann Arbor are over 80 years old, and we have a good system. Then we pipe it in, we use it in the house, we pollute it, we send it out through a sewer pipe. That's not negative.
Right.
So we take clean, we mistreat the source water, the river. We ignore the rain. We count that as stormwater. We don't even use that in our buildings. And we treat it in very apocalyptic terms by calling it stormwater rather than rain. And then we pollute the clean water that we've treated and send it away. So that's net negative water. Net positive water counts the entire system as a whole.
Right, right.
And back to the cost question about that, yes, this system costs a lot. The energy cost is a lot. This is not the ideal system. This is a demonstration of the component part. You could use all kinds of different filtration systems. You can use different systems within buildings, different systems within the neighborhood or municipality. And you can connect all of those in different ways. You could connect on the neighborhood scale. What that system costs is almost guaranteed to be less expensive holistically than the current system. What does it cost to treat PFAS after it enters our waterways? What does it cost to pipe the water up? What does it cost to, all of these little costs that are not being calculated into the water bill? What does it cost to maintain a watershed in a healthy way? That is not being calculated in a fair way right now. And when we do that math, a net negative system is surely more costly than a net positive system would be. And I say surely because we don't really know yet. No one's done the full math. They've done it on energy. They've done watershed analysis in Manhattan, for example, and said that it's going to be cheaper to pay farmers to protect the watershed than it is to build a new treatment plant. So let's pay them $4 billion instead of paying $14 billion over 50 years on a treatment plant. I don't know if those numbers are right, but it's something along those lines. So those kind of analyses have been done, but not of the entire system.
Well, that kind of brings me to my last question. And obviously, when you say cost too, maybe another factor of cost is our health, right? And I know just up the road from you is Flint, and one of the biggest water system failures in our country, I think. And right in our state here. So what thoughts do you have? I mean, obviously there's a huge health burden cost to that now. What thoughts do you have on something like this being able to be applied there, maybe on a more proactive approach before it occurs somewhere else?
Again, so when we do this, when we finally do this holistic analysis of the cost of water, are we counting the one child and the healthcare costs in Flint from lead poisoning? Are we calculating that into the cost of water? We're not. That's a separate line item somewhere else in another spreadsheet. So we need to include that in the cost of water, because if we're counting on governments to protect us from bad design, which linear systems are bad designs inherently, it's a poor idea. So we have to calculate the costs into that if we choose that pathway. Flint itself was a failure of systems design. Nobody talked about it as a failure of a systems design. They talked about it as a failure of governance and a failure of regulations, which it was. But we were playing whack-a-mole with Flint. You know, we don't like the cost of the water from Detroit. We're going to use this other pipe. So we're going to use this other pipe. Oh crap, we didn't change the formulation. That's loosening the lead. We're poisoning people with the lead. Oh crap, we'll change the chemicals to protect the lead. Oh crap, now we've got Legionnaires. You know, one thing after another. This is not just a problem in Flint. It's a problem with water systems all across the country. Ann Arbor has an excellent, it's really a model water system. And yet our pipes, we're at the end of the useful cycle of all the component parts that make up the entire system. 70 to 80% of our parts need to be replaced within the next 10 to 20 years for sure. Some of them are outdated by over a decade and already failing and falling apart underneath the streets. So these are the things that need to be addressed. What's not happening in the dialogue right now is really an honest conversation about what should the schematic of watershed systems look like. Should we design it as part of that watershed system using modern engineering, or should we go back to this 120-year-old, 150-year-old linear system that we just keep adding pipes to and making more and more complicated as the years go on? And as we add brand new pipes, the pipes behind them are aging. Whereas if we had a resilient network of things, as component parts age, you could take them offline at no cost to the network, and then replace them with the best system that's available, better than the first one you installed. So as Detroit rescales, we have to rebuild Detroit just supplying the same amount of water that we did when there were 2 million people in the city. Even if there's only one person on that block, that pipe, that person has to pay for that entire block. What if we were to remove that person from that system and put in a system like this? Then when Brett Little decides to move to Detroit and puts a house next to that other little old lady, the last one on the block, he can now put in another centralized system and say, wait a minute, I can harvest more water than you can. Let's share resources back and forth. And you could have a small pipe that connects to the two. Then 10 more houses come and you build 10 more systems. Or wait a minute, let's build a neighborhood system. Instead of building it inside the house, let's have this little dimple in the earth harvest all the water, and we'll do it there, and then we'll pipe it to there. Let's have a system where all of the toilets flush into a neighborhood system that has these composting systems that are resilient, and if one fails, it diverts to the next one. So no one ever loses sewage or water or clean drinking water because the systems are multiplied. And then you can keep scaling. And then what you end up with in the end of this is this happening everywhere, where you then tie in this network of water that ends up in 10, 20 years from now operating as elegantly as a forested ecosystem. Whereas a centralized system, you just end up with a longer linear system that's more and more damaging and more potential for catastrophe the bigger it gets and the longer you wait. And the cost of repair is extraordinary, into the billions of dollars rather than into the thousands of dollars that each individual system would cost. So I always said during the Flint water crisis, I kept urging people, I said, don't try to solve the entire system. Try to figure out how to get Betty at the end of this street water. If you solve Betty's water problem, you solve her neighbor's problem. And if you solve her neighbor's problem, you solve everyone's problem. But it's got to be from the bottom up, not from the top down. We're still trying to fix the Flint from the top down. And one of the greatest justice tragedies with all of this is right from the beginning, companies like Jamie Reynolds were installing these systems for wealthy people in Detroit. They were just like, screw you, municipality, I can go off grid and be on my own. So they were putting in these systems in Flint so that wealthy people had healthy drinking water from day one. As soon as there was any evidence that the water was an issue, they put in their own systems. So what we're ending up with is privatized healthy systems and no conversation about how we have socialized healthy systems the way the linear system is. So the only people going to be left on these linear systems, and this is true for energy as well. People in California and fire-ridden areas are making their own nanogrids inside their house by putting in solar and battery, right? And then in areas like Flint, so you have a fire, you put in solar and battery if you're wealthy. You have lead in your drinking water, you put in a rainwater and a filtration system. We've got to get away from that. We can't have these privatized systems. We've got to figure out how to make this for everyone. So that's what we're working on.
Right. Yeah. A lot to work on. And you, as we wrap up here, you know, I guess you kind of hinted towards it during our discussion. We had you on earlier in the year before the before the world changed. And so you're working on a community scale project that involves net zero water, among many other things. So before we wrap up, you know, where can people go to contact you and learn more about that?
Yeah, I'm crappy at self-promotion. So we're, if I didn't already introduce it, from the Thrive Collaborative, it's our company. So you can go to thrive-collaborative.com or Veridian@countyfarm.com. That's Veridian with an E. So Veridian@countyfarm.com, or you can just Google my name and you'll find it, Matt Grocoff. And what that is a 13-acre project. We're partnering with Avalon Housing. Avalon is doing deeply affordable 50 units for some of the residents who will recently have experienced homelessness. And then we're doing market rate homes as part of the same neighborhood. And the market rate homes are part of the Living Community Challenge. So the entire neighborhood is seeking net zero energy pedal and some other pedals as well. We won't be doing water because frankly, it's just too much of a cost for us to internalize.
Okay.
If we in the next project, we hope to work with the municipality to do that and create its own water district so the municipality can then show this proof of concept on the neighborhood scale. And then Avalon Housing is doing their community building, their administration building, as a Living Building Challenge Net Zero Energy Affordable Housing pilot project. So they're part of that with Living Future Institute. So it's pretty damn cool. And I got an email a minute before this started from DTE, and we've been talking with the governor's office and the MPSC and with DTE about doing a microgrid. And a microgrid is basically the energy version of what we've been talking about, network energy that flows both ways rather than in a linear fashion.
Great. Well, thanks for sharing that, Matt. It's great to see you virtually, at least anyway. Hope to see you in real life. Thanks for joining us again, Matt Grocoff, Thrive Collaborative. And before we close out, just a public service announcement as always. You know, make sure you've got your masks on. Make sure you social distance. Make sure you can stay away as much as you can. I want to see you all in person here shortly. We need to beat this thing.
What's the other way? Make sure you vote. And make sure you get your friends to vote. You don't want to be asking yourself if the election doesn't turn out the way you'd like it to, if you did enough. Make sure you can answer that you did enough. So get out there in 2021. I really hope we can all see you in person for something. So thank you so much, everyone. Take care. Thanks, y'all. Thank you, Brett. Yep.